Good evening. It is 6 p.m., but participants are yet to join. So we'll wait for a couple of more minutes before we get started. Hi, good evening, and welcome to week 7 of the live sessions for Computational Science and Engineering. This course is taught by Professor Ashok Dey from the Department of Aerospace Engineering at the Indian Institute of Technology, Kanpur. I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. As usual, we'll look at a few key concepts that were pivotal in the contents of this week. Then we'll solve a few illustrative problems that will help us clear our ideas and hopefully make solving the assignments a little bit easier. And it is my hope that it also helps you with the course examination in case you register for it. Now this week we looked at, quite a lot of content was covered, but some of it we had already looked at before, such as the Gauss-Jordan method, the eigenvalue problem, as well as the method of least squares for a line fit. And we also looked at the Gram-Schmidt orthogonalization in quite a bit of depth. So today we'll mostly be looking at interpolation and the integrities of interpolation. The first theorem, which is unnecessary mathematical background, is the Weierstrass approximation theorem. And in fact, this is the one which even makes the idea of, say, an interpolating polynomial feasible. And okay, first the formal statement. So suppose we have any arbitrary function f, which is defined and continuous on the closed interval ab. Then for any epsilon which is greater than 0, there exists a polynomial px of undefined degree here with the property that the absolute difference between the function fx and this polynomial px would be less than this arbitrarily chosen epsilon for all x in the closed interval a and b, which in essence means that for every given, say, arbitrary function, we can construct a polynomial in the same interval, which can be brought, arbitrarily close or can be a reasonably good approximation of the given arbitrary function. It is also depicted here graphically. So you have your function um, fx, which is in black here. So this arbitrary function fx, and you have these bounds above and below fx, which are say at a height of epsilon. So epsilon is in some way the error which you can associate with this function. And within this plus minus error bound, we can define this polynomial function px in blue, which will always be a good approximation of the function and will lie within the error bounds. Of course, as we make the value of e epsilon smaller, that is, we bring these error bounds closer to the function. Maybe we can have a different p, say a p1 of x, which is again a polynomial, which will still lie within these error bounds. And the idea is that a polynomial will always be a good approximation for any arbitrary function. And we examine this idea in greater depth. So why polynomials? Why not any other function such as, say, trigonometric functions, which we usually use in, say, a Fourier expansion of any function? So one reason is that they uniformly approximate continuous functions. And for any given function which is defined and continuous on a closed and bounded interval, there exists a polynomial that is as close to the given function as desired, which we just looked at. We can keep the epsilon error sufficiently small, and we'll still always be able to construct a polynomial function which will lie within those error bounds. Another important reason for considering polynomials is that the derivative as well as the indefinite integral of the polynomial are fairly easy to determine, and even they are polynomials. So whether you are differentiating a given polynomial of a degree, you'll end up with a polynomial of a degree one lower. Depending on the degree of the polynomial, you can differentiate it that many times. Also, when you integrate it, or even you have an indefinite integral of the polynomial, you will end up with a polynomial which is a degree higher. So even with these transformations, we are still working in the domain of polynomials only. And for these reasons, polynomials are often used for approximating continuous functions. Whenever we say approximating, it ensures that, or it inherently implies that there is some error between the exact function we were working with and the approximation. And depending on which interpolating scheme we use, this error may be higher or lower. We did look at uh, errors and preliminaries of, say, machine arithmetic in the previous session. In the previous session, we also looked at Taylor polynomials, which are very often encountered and may consider to be one of the mainstays in calculus. And thus, it is not unreasonable to think that maybe Taylor polynomials have a big role to play even in approximation of functions. But that will not be true. That is because the Taylor polynomials agree very closely or as closely as possible, depending on the number of terms you are willing to account for with a given function, but only at a specific point. They concentrate their accuracy near that point. However, if you want to have a good interpolation polynomial, and when we say interpolation, what we mean is that, say, here you have a simple representation of data. Say you have few discrete data points, and you want to know, assuming that this distribution of data does have some sort of functional relationship, want to know that what can be a good reasonable approximation, say at this x right here or at any other where you don't have a data in between. So ideally what you want to do is you want to interpolate between these points. So maybe there is a function ideally continuous and differentiable throughout, which can be fitted to these data points and which will give you a reasonably good approximation at your desired point of interest. Of course, this is a highly subjective assumption. I mean, it might well have been these straight lines, in which case our approximation goes out the window. But then that is not for us to know beforehand. It's as good as it gets. It's interpolation because we are still within the domain or the interval across which we have data points. If we were trying to say forecast or predict based on available data, and we want to say look at a point x here, it would be extrapolation because now we have data points on information only in this domain. But we want to extend our predictions beyond it. Any good interpolation polynomials would need to provide a relatively accurate approximation over the entire interval or the entire interval of definition of the data points. Whereas Taylor polynomials have very good accuracy but only at one given point. Secondly, for Taylor polynomials, all information used in the approximation is concentrated at the single number x naught or the number or point about which we are expanding the Taylor polynomial, and they will generally give inaccurate approximations when you move further away from x naught, and the further away you are, chances are the more inaccurate or the more erroneous your approximation becomes. And this really limits the Taylor polynomial approximation to situations in which approximations are needed only at numbers very close to x naught. Say, if we have a discretized domain, in case we are interested in information only very close or very nearby to any given point of interest, Taylor polynomial might still be good enough, but that is not usually the case. And for most ordinary computational purposes, it is often more efficient to use methods that include information at various points. The most elementary of such is a Lagrange interpolating polynomials, and we have a mathematical definition here. So if you are given data points such as x naught, x1 till xn, there will be n plus 1 distinct numbers, and f is a function whose values are given at each of these numbers. So you have information of say x naught, fx naught, x1, fx1, and xn, fxn. You have this data set of n plus 1 points. Then a unique polynomial px of degree at most n exists such that the value of the function is equal to the value of the polynomial at the same points for all xk where k varies from 0 to n. And this polynomial p of x is given by the Lagrange polynomial, which is f of x naught times L n0x. So this n simply denotes the degree of the Lagrange polynomial. We'll be skipping this notation because it is cumbersome to write. And each of these Lagrange coefficients of order n for the kth term is defined as such. It is simply a summation or a series of products. Now, given that this has already been covered in the lecture and the formula is readily available to us, we'll try to construct some simple uh, approximations or try to construct some simple Lagrange polynomials. So here we have a given information set where we have three nodes, x naught equals 2, x1 equals 2.75, and x2 equals 4. And we have to find Lagrange interpolating polynomial for the given function fx is 1 by x. We can also write this down. F of x naught is 1 by 2, which is 0.5. F of x1 is 1 by 2.75. Just use a calculator for this. Just 0.36 recurring. And f of x2 is 1 by 4, which is 0.25. Now, when we are to find Lagrange polynomial, first we might first we must find these coefficient polynomials, which are simply LKs. So let's start with that. For k equal to 0, the using the formula available, it can be constructed. We have three data points, so n plus 1 is 3, which implies that n is 2. So this will be a second order Lagrange polynomial. For the first case, just using the formula in the previous slide, first data point is 2, so 2 minus uh, similarly for L1 of x, I think sorry, this comes out to be 1, 2 times 2.75 minus 16 by 15. times x minus 2 and x minus 4 for k equals to L2x will be x minus 2, x minus 2.75 by 4 minus 2, 4 minus 2.75. It turns out to be 2 by 5 times x minus 2 and x minus 2.75. Now, once these coefficients are determined, we are ready to construct our polynomial. So we are going from 0 to 2, f of xk, lk of x. So this is implies f of x naught, L naught of x, L of we have already, yeah, might as well expand it for clarity. So the first is 1 by 2 times 2 by 3 x minus 2.75 x minus 4 plus 0.36 recurrence. Let's see if I can express that in 1 divided by 2.75 is 4 by 11. So 4 by 11 into minus 16 by 15 into x minus 2 times x minus 4 plus the third is 1 by 4. 1 by 4 times 2 by 5 x minus 2 x minus 2.75. If we just continue expanding, so this will be 1/3 x minus 2.75 x minus 4 minus 64 by 165 x minus 2 x minus 4 plus 1/10 of x minus 2 times x minus 2.75. And usually we can leave it at this, but just in case we want to just expand all the terms further, this will turn out to be 1 by 22 times x square minus 35 by 88 times x plus 49 by 44. So we end up with this polynomial, which is really a second order because the order can be at most n, where n plus 1 is the total number of data points, which in this case was 3. So we already knew that we will be ending up with at most a quadratic polynomial, and that is what we have. The second step or the second part of this question is that we have to use this polynomial to approximate f at 3 equals 1/3. So let us calculate the value. I will do it on the next page. p at x equals 3. So this will turn out to be 1 by 22 times 3 square minus 35 by 88, 3 plus 49 by 44, which is 9 by 22, 15105 by 88 plus 49 by 44, which will come out to be 29 by 88, or in decimal 0.32954. And the original function value is already given to us. It is 1/3. So our approximation is 0.32954. The actual value is 1/3, so 0.33333, recurring of course. And let us look at our errors. So the absolute error is 0.33333 minus 32954, 0.379 into 10 power minus 2, and our relative error comes out to be 0.011. So this was a simple example where for a given data set, we constructed the Lagrange interpolating polynomial, and we also compared how well of an approximation it makes for a given functional value. Another thing to look at is the divided differences scheme, and we have the definitions here. So the zeroth divided difference of function f with respect to xi is simply the value of f at xi. The remaining divided differences are often defined recursively. So we must have the preceding divided difference before we can actually compute the next ones. So the first divided difference will actually be defined in terms of the zeroth divided difference, and the difference between of f of xi and xi plus 1 is simply the functional value at xi plus 1 minus functional value at xi by xi plus 1 minus xi. We use the first divided differences to define the second divided differences, where the second divided difference of xi plus 1 and xi plus 2 is f of xi plus 1, xi plus 2 minus f of xi plus 1 by xi plus 2 minus xi plus 1. To compute this, we go here, and to compute this, of course, this is just the functional value, but the idea is the same. And we can keep on doing this till the nth divided difference, which will again utilize the definition of all previous ones. And suppose that Pn of x is the nth Lagrange polynomial that agrees with the function of the distinct numbers x0, x1 till xn, so the n plus 1 numbers. And while this polynomial is unique, there may be alternate algebraic representations which prove useful in certain situations. And the divided differences of f with respect to x0, x1 till xn are used to express Pni in this form. So we can also obtain the Lagrange interpolating polynomial in terms of the divided differences. And this representation may have its own uses in few specific cases. And such a representation is given here. So usually you will have it in this typical form. And in the divided differences form, Pn would be f at x0 plus f of x naught comma x1 times x minus x naught plus so on and so forth, where these a2, a3, an have to be computed. A0 turns out to be simply f of x naught. A1 turns out to be the first divided difference, f at x naught comma x1, and the remaining required constants similarly. Any ak is the kth divided difference, or f at x naught, x1, x2 till xk. And in the Newton's divided difference form, the Lagrange polynomial Pn can be expressed as such. And it is very interesting to note that the value of the kth divided difference is independent of the order of numbers x0, x1 till xk. It does not really matter which order we are taking. And here we have a ready table which might serve as a reference later on, where we have the numbers x, the value of the functions x, also the zeroth divided difference. Then using these zeroth divided difference, we have definitions of the first divided difference. Using the definition of the first divided differences, the second divided differences are listed, and similarly to the third. And such a recursive table can be constructed. So maybe we can go till the fourth and the fifth. Here we have six data points, n plus 1 equals 6. So we can have till the fifth divided difference. And we will do just that. So this question asks us to generate the divided difference for this given table of data, and to also construct the actual polynomial which will use this data, or which can be used to approximate this data. So we just looked at the definitions. So let's get started. The zeroth divided differences are already given to us, so we will not need to compute that. Compute the first divided differences. Point 62008660 minus 0.7651977 by 1.3 minus 1.0. I'll just use a calculator for this. This can also be very easily done, say in a spreadsheet like Excel. This comes out to be minus 0.4837057. Let us just compute a few more for practice. So x1, x2 will be f of x2 minus f x1 by x2 minus x1, which is 0.4554022 minus 0.6200860 by zero point 0.3, so the nodes are evenly spaced here. This comes out to be minus 0.548946 0. And just compute one more. So f of x3, x2 will be f of, sorry, while the order does not matter, it's best if we stick to our convention. And 2818186 minus 0.455402 by 1.9 minus 1.6. This turns out to be minus 0.578612. There's one more which can be similarly computed. I'm not doing it. Now let's compute the second divided differences. Okay, we have ample space. So the first would be x naught, x1, x2. So will come out to be f of x1, x2 minus f of x naught, x1 by x2 minus x naught. We have already computed these values. So f of x1, x2 is minus 0.548946 minus x naught, x1 is 0.483757 by zero point 0.6, 1.6 minus 1.0, 5489460 plus 37057 divided by 0.6. That will be minus 0.108733. Let us compute one more. So f of x1, x2, x3 will be f of x2, x3 minus f of x1, x2 by x3 minus x1. F of x2, x3 is minus 0.578612. F of x1, x2 is minus 0.548946. 1.9 minus 1.3. Four, 89460. This turns out to be minus 0.0494433. Similarly, the other one can be computed, except it will require this value. So I'll leave it as an exercise. X2, X3, X4. Now we can move on to the computation of the third divided difference. And we have 5 data points for even the fourth divided difference. F of x0, x1, x2, and x3. And this is a recursive scheme, so it's pretty easy even if the terms look intimidating. We just have to ensure that whatever values we obtained in the previous steps were correct. Because if you have error in one of the steps, it'll propagate everywhere because of the recursive nature of the method. Sorry. We have f of x1, x2, x3, which was minus 0.0494433. X0, x1, x2 is minus 0.1087338. 0.9, so 1.9 minus 1.0. This comes out to be positive 0.0658783. Of course, we can't calculate the other one because we have not calculated these values right here. So again, left as an exercise, there'll only be two third divided differences. So this one would be x1, x2, x3, and x4. And without it, we are not in a position to calculate the fourth divided difference either. So maybe you guys can do it as an exercise and see what value you end up with. Of course, it's not very difficult because you already calculated values of most of the preceding values needed. I'll just write the formula here. X2, x3, x4 minus f of x0, x1, x2, x3 by x4 minus x0. And just to verify, this will turn out to be 0.0018251. Now, once we have these coefficients, we can very easily calculate the polynomial or the interpolating polynomial. is a fourth order because we had five data points. So the first one will simply be f of x naught, 0.76 51977 minus 0.483 7057 times x minus x naught, so 1 minus 0.108 7338 x minus x naught, so 1.0 and 1.3, and x minus x1. This is positive 0.0658 783 x minus x naught, x minus x1, x minus x2, and finally the last term 0.0018251 x minus x naught, x minus x1, x minus x2 times x minus x3, 1.9. And this right here is the interpolating polynomial. Again, just like last week, I'll also supply pseudocode for this for implementing the Newton's divided difference formula into a code. Again, pseudocode is just the algorithm in say easy to understand and in a human readable form. The difference between a code and a pseudocode is that often a code will be written in some specific programming language, and thus it will be say rigidly coupled to the syntax and semantics of that language. Usually the syntax of say any two languages such as C and Python, or say a MATLAB script in Python, will not be the same. They will have some semantic differences. Thus, one code, uh, if simply rewritten in some other programming environment, will often lead to errors. Whereas a pseudocode is simply consists of logical statements, which uh, we the users have to implement into our programming language. And thus, it's say a more open or a more readable format. So whenever we are writing a pseudocode, we must be clear with the objective. Here, the objective is to determine or to obtain the divided difference coefficients of the interpolating polynomial, which was px. When we are given, say, n plus 1 data points, and we are constructing the nth order polynomial. Also, either we have the function, in which case we can like explicitly calculate the values of the function at each of these data points, or the data may be supplied to us, say, as a CSV table, which has both x and y data. Either way it works. The input for this code will be the numbers, sorry about that, x naught, x1 till xn, and the functional values or the function. of x naught, f of x1, f at x1, and so on till xn. For this pseudocode, say they're defined as f of 0, 0, f1, 0 till f of n 0. The output which we expect from this code will be the polynomial itself. And so let us write the steps. The nested loop. So within I we have the j loop 1, 2 till I f of ij equals fi j minus 1 minus fi minus 1 j minus 1 by xi minus xi minus j. And just as a comment here, fi comma j is referring to the divided difference. More space till xi. Once this computation is complete, we simply skip to the next one where we output these. The first uh, the first column, which is the zeroth column, f00, f10, f20 till fn0 is already supplied to us in the form data points. Those are already available, and the rest we have calculated in the preceding loop. You see, these are all the diagonal elements. So if I write one more, this is f22, and it is actually the diagonal elements which act as the coefficients of these terms of the polynomial. That we're only interested in the diagonal elements. Of course, to compute those diagonal elements, we need the off-diagonal elements as well. Once you have these coefficients, you can simply say construct a polynomial or multiply them or use them as such. And so the algorithm will stop here. Now, when we are working with divided differences, we can have either a forward divided difference, where we say we are calculating f of x1 minus f of x naught, a backward divided difference, where the sequence will be reversed, or even a centered divided difference. And depending on the scheme which you are using, the final interpolating function will differ, say usually by a small amount, but still significantly. And each may have different implications on the results which are obtaining. So they are also formulated here. The forward difference formula we already looked at, and it often uses the del notation introduced in Aitken's del square method. And in terms of this notation, it is written as 1 by h del f of x naught, where h is the step size. Similarly, the second divided, so this is the first divided difference, this is the second. In the Aitken del square notation is written as 1 by 2h square del square f of x naught. And in general, any kth divided difference shall take the form f at x naught x1 xk is equal to 1 by k factorial h power k uh, del power k f of x naught. And in this notation, the Newton forward difference formula is given here for your reference. Similarly, we have the backward difference. where if the interpolating nodes are simply reordered from last to first at xn minus 1 till x naught, we can write the interpolator formula in a different fashion. And assuming that the nodes are again equally spaced at a spacing of sh, we can have the interpolating polynomial in the formula given. And in such a case, the Newton backward difference formula is given here just for your reference. Similarly, we can also have something called a centered difference formula, which in most cases proves to have say less error than either the forward or the backward, because in a way we are going taking the middle road here. And one of the formulas called Stirling formula is also given here for your reference. So some drawbacks of the forward and backward difference formula are that they're not appropriate for approximating fx when x lies near the center of the table. When it says table, it means center of the data set which we have, because neither will permit the highest order difference to have x naught close to x. And there's a number of divided difference formulas are available, and depending on the situation, we may pick one. These methods are known as centered difference formulas, and one of the well-known one is Stirling's method or Stirling's formula. Now, for this centered difference formula, we choose x naught near the point being approximated and label the nodes directly below x naught as x1, x2, and so on, and directly above us x1, x minus 1, x minus 2. So previously we had our data points in this fashion. For Stirling method, what we do is wherever our region of interest is, that node itself becomes x1. The ones coming after are numbered subsequently, and the ones coming before take on negative indices. And utilizing this convention, the Stirling's formula is given here in equation 3.4. And this is true for n odd n. If the number n is even, this last line will go out. So a useful footnote. Okay. So the next interpolating scheme which we'll use is something called a class of polynomials called Hermite polynomials, and they come from a general class of polynomials known as osculating polynomials. These polynomials actually generalize both the Taylor and the Lagrange polynomials. And in a situation where we're given n plus 1 distinct numbers and non-negative integers m0, m1 till mn, where m is maximum of these, the oscillating polynomial approximating a function f, which is continuous, m continuous on the closed interval ab at xi, is the polynomial of least degree that has the same area as the function f, and all its derivatives are of order less than or equal to mi at each xi. And the degree of this oscillating polynomial is defined as such. Now, similarly, let x0, x1 till xn be n plus 1 distinct numbers in the closed interval ab, and suppose that f is m continuous on closed ab. The oscillating polynomial approximating f is the polynomial px of least degree such that the kth derivative dk dxk of pxi is equal to the kth derivative dk dxk of f of xi for each I equals 0, 1 till n, and for each k equal to 0, 1 till mi. And from this general class of oscillating polynomials, we define the Hermite polynomials, where if f is first continuous on the closed interval ab and x0, x1 till xn belong to the closed interval ab and are distinct, the unique polynomial of least degree agreeing with f and f prime is the Hermite polynomial of degree at most 2n plus 1. So previously we were only dealing with polynomials of degrees lower than the given number of data points. Here the degree of the polynomial is higher, and the Hermite polynomial is defined as given here. So for the degree 2n plus 1, the Hermite polynomial is equal to the sum of 0 to n f of xj h n jx plus sum 0 to n f prime at xj h cap at nj of x. Again, if f is continuous, 2n plus 2 continuous on AB, we have approximation of fx, which has the Hermite polynomial of degree 2n plus 1, as well as the error or remainder term for some generally unknown zeta x on the interval open AB. We will also construct a Hermite polynomial for the given dataset after a short break. So let us reconvene in say 10 minutes. So let us continue. We looked at the formulation of the Hermat polynomial. Let us construct a polynomial for a simple case where we have these three data points. The values of the functions and the derivatives are already supplied to us. As you saw in the formula, this will include the Lagrange coefficient polynomials as well as the derivatives of the Lagrange coefficients. So let us quickly compute those. So we have three data points. So we will have so our Lagrange polynomial will be an order 2. This turns out to be 50 by 9 minus 1.6 x minus 1.9. And if we simplify it further, what we'll end up with is 50 by 9 x square minus 175 by 9 x plus 152 by 9. Let us compute the derivative here only. So this will turn out to be 100 by 9x minus 175 by 9. The next Lagrange polynomial L1 minus 100 by 9 x minus 1.3 x minus 1.9. And if we expand this further, this will come out to be minus 100 by 9 x square plus 320 by 9 x minus 247 by 9. Its derivative will come out to be minus 200 by 9x plus 320 by 9. The third one, minus x naught, x2 minus x1, 1.3 x minus 1.6 by 1.9 minus 1.3 minus 1.6, 50 by 9 times x minus 1.3 x minus 1.6, which turns out to be 50 by 9 x squared minus 145 by 9x plus 104 by 9, and its derivative again 100 by 9x minus 145 by 9. Once we have the Lagrange polynomials and the derivatives, we are ready to compute the Hermite polynomial itself. So we calculate the terms of the Hermite polynomial separately. Not right. Yes. So we calculate these h n j's and h hat n j's. Now h20 of x 1 minus 2 x minus xj l prime n j xj ln j square of x. We use the same formula 1 minus 2 x minus 1.3 minus 5 the derivative and if this were to be simplified this will turn out to be 10x minus 12 times 50 by 9 x square plus 175 by 9x plus 52 by 9 whole square. Similarly, the next term s21 is 1 times minus 100 by 9 x square plus 320 by 9 x minus 247 by 9 whole square. The term s22 of x is 10 times 2 minus x 50 by 9 x square 45 by 9 x plus 104 by 9 whole square. Let us calculate the h hat terms. This will turn out to be x minus 1.3 h hat 21 comes out to be x minus x1 so 1.6 and the last one h hat 22 x minus x2, which is 1.9, times 50 by 9 x square minus 145 by 9x plus 104 by 9 square. The order of the Hermite polynomial, if you remember, is 2n plus 1. Here n plus 1 was 3, so n is equal to 2, so this will be 5. So the fifth order Hermite polynomial will be 0.620086, is this value right here, h20 of x is 0.4554022, 0.4554022, h21 of x plus 0.2818186, 0.2818186, h22 of x minus 0.5220232 minus 0.5220232 h hat 20 minus 0.5698959, 0.5698959 h hat 21 minus 0.5811571 h hat 22. This is the Hermite polynomial. There is a part where we are trying to us to find an approximation at x equals 1.5. For that, each of these terms will have to be calculated separately. And I'll just give out the final answer and it can be verified by you guys. So for an approximation at x equals 1.5, the fifth order Hermite polynomial will turn out to be 0.5118277. But please verify it. There might be some mistakes in my calculation. And if you do indeed come across a mistake, do inform me as well. But it should come out to be this. And this was pretty intensive, so having a pseudocode will help in case you ever want to use it or encode it yourself. So when we are working with Hermite polynomials or Hermite interpolation, the objective is, say, in its construction is to obtain the coefficients of the interpolating polynomial given n plus 1 data points and the function f or the functional values of at each of these data points. So in this case again, say the input will be the numbers x0, x1 till xn, and the values or the function will also do. If only the function is given, we must compute these values explicitly. And this scheme also uses the derivatives, so we must also have the derivatives at each of these points. If not, they must be calculated explicitly. And the intended output of this scheme would be the coefficients of the Hermite polynomial. So they go to 2n plus 1 and 2 plus 1, which will define the Hermite polynomial as q00 plus q11 x minus x naught plus q22 x minus x naught square plus q33 plus x naught square x minus x1 plus q44 x minus x naught square x minus x1 square. This goes on the term q2n plus 1 2n plus 1 x minus x naught square x minus x1 square. This product continues to go until x minus xn minus 1 square x minus xn. And the algorithm for this, for I equals 0 to n, we perform the succeeding steps. Z to I plus 1 equals xi as well. Q to I comma 0 equals f of xi. Q of 2i plus 1 comma 0 equals f of xi. Q of 2i plus 1 comma 1 equals f prime of xi. Now, if I is not equal to 0, qi q2i minus 1 comma 0 by z2i minus z2i minus 1. Now the second loop, which is nested for j equals to 3 li, we set qij equals qi j minus 1 minus qi minus 1 j minus 1 by zi minus zi minus j. Step 5, we output all of these Qs. So again, interested only in the principal diagonal elements. And then we stop. The steps that we are supposed to repeat are steps 2 and 3. Now, this is a very involved pseudocode, so it is not something I have written myself. I have borrowed it from several sources, and it should turn out to be correct. But in case of any errors, please do let me know. Okay, the next topic that was touched upon this week was piecewise interpolation. So previously, whatever we were looking at concerned the approximation of the arbitrary functions on given closed intervals using only a single polynomial. However, when we are dealing with high degree polynomials, they can oscillate erratically, and any minor fluctuation over a given small portion of the interval can actually induce rather large fluctuations over the entire range, leading to errors. Thus, rather than using only a single polynomial for approximating a function, what we can do is we can divide the given interval into a collection of subintervals and construct a usually different approximate polynomials for each subinterval based on the say the need. In subinterval, the variations may be quite simply modeled or simply approximated, whereas in some given subintervals, they might be more intricate. So for each of these intervals, we can have a polynomial or an approximating function which suits the level of complication. And this is called a piecewise polynomial approximation. The simplest piecewise approximation would be piecewise linear interpolation, which simply means that you join them by straight lines. However, a very clear disadvantage of the linear approximation is that there is likely no differentiability at the endpoints, because usually when you are joining these points by straight lines, say between any 2 points, you draw these straight lines. While the final function we get is continuous at the intermediate points, it is not differentiable because of the sharp change in value. And of course, geometrically, this would imply that the interpolating function is not smooth. It has these jagged points at all of these intermediate interval points. And often the physical conditions of a problem that we are trying to model will necessitate smoothness at each of these intermediate points. That is, despite assuming different functions for different intervals, they must still be both continuous and differentiable at the intermediate points. Thus, the approximating function must be continuously differentiable. And when we are looking at piecewise interpolation, often the most commonly used uh, approximation scheme uses cubic polynomials and is called a cubic spline interpolation. And when you are working with a cubic polynomial, you will have four constants, that is the coefficients of the third order, second order, first order, and zero third order terms. And thus, there is sufficient flexibility in the cubic spline procedure to ensure that the interpolant is not only continuously differentiable on the interval, but also has a continuous second derivative. Now, given a function f defined on the closed interval ab and a set of nodes which are ordered such that x naught is less than x1 is less than x2 is less than xn equal to b, the cubic spline interpolant s for f is a function which satisfies all the following conditions. So there are actually six. Two are on the next page. I can add the following six conditions. Sx is a cubic polynomial denoted as j of x on the subinterval xj plus 1 for each j equals 0 to n minus 1. Sj at any point xj is equal to the functional value f of xj, and Sj at any point j plus 1 is equal to the functional value of j plus 1 for each j. This will simply mean that whatever interpolating polynomial cubic spline we are using between any two points in the subinterval, the cubic spline has a value equal to the functional value at either endpoint. Similarly, Sj plus 1 at xj plus 1 is equal to Sj at xj plus 1. That is, if I have these subintervals, I have one cubic polynomial here. The value of the second cubic polynomial as well as the derivative should be the same at this intermediate point. Okay, maybe not the best representation because this will imply that there is some degree of discontinuity, but maybe like this. Similarly, S prime j plus 1 at xj plus 1 equals S prime j at xj plus 1. That is, two successive or two nearby interpolating splines have the same derivative at a given point, the first derivative. Similarly, the second derivative S double prime j plus 1 at any point xj plus 1 should equal the second derivative S double prime j at the same point xj plus 1. And either one of the following set of boundary conditions should be satisfied. Either S double prime at x naught, that is one end of the interval, equals S double prime at xn, that is the other end of the interval, equals 0, that is referred to as the natural or free boundary condition, or the first derivative x prime at x naught equals f prime at x naught, and s prime at xn equals f prime at xn, which is the clamped boundary condition. What are the implications of the term natural and clamped is also given here. So a natural spline has no conditions imposed for the direction at its endpoint. That is, the second derivative is 0. So the first derivative is a constant, and which implies that the function itself is linear at the endpoint. And the curve takes the shape of a straight line after it passes through the interpolation points nearest to the endpoints. And it is called natural because this is the natural shape any flexible strip will assume if forced to pass through specified interpolation points without any additional constraints. However, when we are referring to a clamped boundary condition, what happens is clamping a spline indicates that the ends of the flexible strip are fixed so that it is forced to take a specific direction at each of these endpoints, specified usually in terms of the function itself. This is important when two spline functions should match at their endpoints, and it is done mathematically by specifying the value of the derivative of the curve at the endpoints of the spline. Okay, this slide got repeated somehow. The derivation of spline has already been looked at in the lecture. So we'll directly proceed to say constructing a cubic spline for a given data set. So here our data points are 1, 2, 2, 3, and 3, 5. So we'll have two cubic splines. One between, I mean, one for the interval 1 comma 2. So this is x0, this is x1, and the second for 2 comma 3. So let us denote them as such. A naught plus b naught x minus 1 plus c naught x minus 1 square plus d naught x minus 1 cube. Similarly, the other spline can be noted as this. So a1 plus b1 x minus 2 plus c1 x minus 2 square plus d1 x minus 1 cube. Sorry, x minus 2. Now, all of these coefficients a naught, b naught, c naught, d naught, and a1, b1, c1, and d1 must be determined, and they can be determined from both the function values and the derivatives. So the function value at 1 is equal to 2, which must be equal to a naught. Similarly, the function value at x equal to 2 is equal to 3. This must be equal to a naught plus b naught 2 minus 1 plus c naught 2 minus 1 square plus d naught 2 minus 1 cube, which is equal to a naught plus b naught plus c naught plus d naught. The functional value at x equals 3 is equal to 5, which is equal to. Oh, we also have a second condition. Oh, we can do that later. We'll do it right away. So, utilizing this S1 equation, we also have f at x equal to 2 should be equal to 3 for S2 as well. And this will give us A1 plus these other terms go to 0. It simply leaves A1 equals 3. Now, utilizing the other data points, we can have f at x equals 3 is 5, which is equal to A naught plus B naught 3 minus 1 plus C naught 3 minus 1 square plus D naught 3 minus 1 cube. And similarly for the other spline, A1 plus B1 3 minus 2 plus C1 3 minus 2 square plus D1 3 minus 2 cube, which implies that plus B1 plus C1 plus D1. Okay, the first spline does not really pass through x equals to 3, so this condition will not exist. I'm sorry. Line S naught is passing through points interval 1 comma 2, so it'll only have this is for S naught, this is also for S naught, this is for spline S1, and this is for spline S1. So we have four conditions and eight unknowns. Now two more will come from the agreement of derivative at the data points. So we know that S naught, the derivative of S naught at point 2 should be equal to the derivative of S1, first derivative of S1 at point 2. Derivative of S naught at 2 will be B naught plus 2 C naught x minus 1 plus 3D naught x minus 1 square at x equals to B1 plus 2 C1 x minus 2 plus 3D1 x minus 2 square at x equals 2. This will give out B naught plus 2 C naught plus 3D naught equals B1. These terms go to 0. So just this. And since this is a cubic, so the second derivative will also exist. So the second derivative at x equals 2 should also be the same. The second derivative will have 2c naught plus 6d naught x minus 1 at x equals 2 equals 2c1 plus 6d1 at x minus 2, which implies that 2c naught plus 6d naught equals 2c1, as this second term goes to 0. So we have 1, 2, 3, 4, 5, and 6 conditions till now. We still need two more if we have to determine all the eight. Two more will come from the boundary condition. So the question mentions that we are trying to construct a natural cubic spline. When you have a natural cubic spline, the second derivative at the end intervals, at the end points, is equal to 0. So S naught double prime at x equals to 1 will be 0, which implies that 2c naught plus 6d naught x minus 1 at x equals 1 shall turn out to be 0, which implies that 2c naught is 0, and the second term will go to 0, or c naught is 0. This is our seventh condition, and s1 double prime at the other endpoint, which is x equals 3, is 0. Yes. So two C1 plus 6 D1 x minus 2 at x equals 3, 0, which implies that 2C1 plus 6 D1 is equal to 0. This is the eighth condition. So now we have 8 unknowns and 8 conditions. I mean, theoretically, it is possible to solve them, even though it is not perhaps the most straightforward, but it can be done. Once we do it, what we'll find is we already have A naught, which is equal to 2, and we have A1 equal to 3. C naught is 0. We don't have ready values for the remaining, but if you do it, what will come out is B naught will be 3 by 4, and D naught will turn out to be 1 by 4. Similarly, B1 will be 3 by 2, C1 will be 3 by 4, and D1 will turn out to be 1 by 4 as well. So the cubic spline S naught will equal A naught plus A1 plus B naught x minus x naught plus C naught x minus x naught square plus D naught x minus x naught cube, which will turn out to be 2 plus 3/4 x minus 1 plus 0 x minus 1 square plus 1/4 x minus 1 cube, and S1 will turn out to be A1 plus B1 x minus x1 plus C1 x minus x1 square plus D1 x minus x1 cube, which will be 3 plus 3 by 2 x minus 2 plus 3/4 x minus 2 square plus 1/4 x minus 2 cube. These are the piecewise cubic polynomials. And we can also define the approximating function overall. If we denote it by Sx, it is equal to 2 plus 3/4 x minus 1 plus 1/4 x minus 1 cube for x in the subinterval 1 to 2, and equal to 3 plus 3 by 2 x minus 2 plus 3/4 x minus 2 square plus 1/4 x minus 2 cube for x belonging to the other subinterval close 2 to close 3. And this is the cubic spline interpolation for this simple data set. Of course, I had coded it before, and so I used the code to obtain these coefficients. I'll also share the pseudocode for this natural cubic spline with you. So when we are looking to code a natural cubic spline, Our objective is to get the interpolant function itself given at the given data points. So x naught, x1 till xn, and since it is natural, the second derivative at each of the extreme endpoints should be set to 0. So the input in this case will be the number of data points and the order of the polynomial is cubic, of course. The data points itself, x0, x1, x2, xn, and a0, a1, which will turn out to be the value of the functions themselves. The output, which we can expect from such a code, are the other coefficients. So all the AJs, BJs, CJs, and DJs for j equals 0, 1 till n minus 1. Of course, some of these are already known to us, which are A0, for instance, A1, and so on. And just for reference, any QA polynomial, the spline will be defined as this equal to AJ plus BJ x minus xj plus CJ x minus xj square plus DJ x minus xj cube for all xj less than equal to x less than equal to x j plus 1. So the algorithm in the first step for I equals 0, 1 till n minus 1, we set the say the step size h is I plus 1 minus xi. Usually the domains are discretized such that the step size is even throughout the domain, or all subintervals we choose are of equal size. Step 2 is for I equals 1 to till n minus 1. We set this parameter alpha is 3 by hi, ai plus 1 minus ai minus 3 by hi minus 1, ai minus ai minus 1. We set another parameter L naught equal to 1, mu naught equal to 0, and Z naught equal to 0. What these parameters mean, I'll come back in the end. So the fourth step is that for I equals 1 to till n minus 1, you again update the value of these parameters. So Li is equal to 2 xi plus 1 minus xi minus 1 minus h I minus 1 times mu of I minus 1. The value of mu I is also updated to hi by li. And the value of the parameter zi is alpha I minus hi minus 1 z I minus 1 by li. In the fifth step, these values are updated again. So, okay, no, these are just the ln values. So ln zn is equal to 0 and cn is equal to 0. We similarly defined L naught, mu naught, and Z naught. In the sixth step, for j equals n minus 1, n minus 2 till 0, we set Cj equals Zj minus mu j Cj plus 1, Dj equals Aj plus 1 minus Aj by Hj minus Hj times Cj plus 1 plus 2 Cj by 3 and Dj equals Cj plus 1 minus Cj by 3Hg. The seventh step gives us the output, which are the numbers Aj, Bj, Cj, and Dj for all j's. So j going from 0 to n minus 1, then we stop. So these parameters alpha, L, mu, and z actually they are coming from the solution of uh, so alpha, mu, L, z, they are coming from the solution of tri-diagonal linear system from something called a tri-diagonal matrix algorithm or TDMA solver. And this is a common solution strategy. It might also be touched in the course itself. I'm not sure. Maybe in the contents of the upcoming week. But this is a quite a frequently encountered solution algorithm where we have our values of interest in a tridiagonal matrix. And this is a standard method to solve such a linear system. Okay, we have already exceeded our time. We still had to look at the clamp cube experiment. Maybe we can do it next week. So that's it for now. All right. Thank you for tuning in to the live sessions for computation science and engineering, and see you all again next week. Thank you.
Thank you, Saurav.